All right, my name is Nathan Faubion. I've been programming in PureScript for almost 2 years now, professionally as well, full time. So it's been a pretty nice road to get here. But I wanted to talk on async programming in PureScript, and hopefully this isn't like too advanced. Like if you're kind of intimidated by some of it, I won't get like, it's kind of a whirlwind tour a little bit, but and if there's anything that's kind of confusing, like there's some PureScript syntax stuff and like that, but hopefully we can kind of, some of the ideas can propagate. So I kind of like started with like this kind of quote that people kind of say a lot is like, functional programming is great for data processing when you've got things that are kind of, or programs that are modeled as pure functions, or like a compiler or something, that we have like a clearly defined input and a clearly defined output. It's like great. But like as soon as you like get like gnarly business logic and effects where you got to like do all this stuff, coordinate things, it's like, it's kind of like there's like this idea that it breaks down, but I don't think that's true. And I think that for pure functional programming especially has a great way for dealing with these problems. And so one of the like, this isn't the only idea of like what it means to be pure functional, like a purely functional setting, but I think like especially for this talk, like this is one of the big ideas that I kind of want to get across, is that like it's kind of weird, this idea that you don't have ambient effects. It's like when in a normal language like Python, JavaScript, it's kind of like the effectfulness of your programs is kind of like baked into the language. In fact, like JavaScript, the spec has like a whole slew of like specifications for how things execute and how like effects get scheduled and all these sorts of things. And so when you do in a purely functional setting, you have to kind of like forget about this idea that you can have just effects anywhere. And so like in an example of an impure functional language might be like OCaml, where you'd see like these functions. These are just function signatures. We have a function like open in string to in channel. It's like a input channel, input line. There's no difference between these functions and something. So like print string a string to unit. You could write a const function. That was just like always return unit. That took a string and always return unit. But this type signature would be identical, and there's no distinguishing the two. And so in an impure language, effects are part of evaluation. And usually you have language level support. So like in OCaml, there's even like imperative sequencing, like the semicolon operator is a way to kind of bundle a series of statements together in functional language, but also it's pervasive. So this idea that effects don't show up in a type signature anywhere. At any point, you could have any effect going on, and there's no way to distinguish the difference between something that's pure and something that actually does something that you might not want to happen. So in a purely functional setting, all we really have is kind of like data. Like you've got functions, and the functions aren't really data, but when it comes to like describing things, like all you really have is like we've got like data constructors and primarily data structures. And when I say like data structures, it's things where we can like put our own things into them. So we have things like array A. So we got an array of whatever we want, and strings. Same with like lists or maps from some key to A. And so one way we might start thinking about effects in a purely functional setting is like, how can we describe these things? How can we like model the effects we want to happen? So this is where this idea of effects as data comes in. So we might start with same thing like a data structure like we had before, like with array or list. We might start with effect of some A. I want effects that return whatever I want. I might have an effect that returns a string or an int. So it's polymorphic over what it can produce. So we're going to kind of like mimic this like OCaml API. So one of the operations is like opening a file, and in the OCaml API, it's just like string or path to whatever, like the channel, like the input. It's just a file handler or like a stream handler or something. And so open file is like our operation. It contains a slot for the path we want to open, and then it has. You think about like sequencing in a purely functional. If you don't have like language support for statement sequencing, like what do you do? So one way to do that is just to take a callback for, like, you want to get, the open file takes a path, but then it also takes a callback. And in that callback, you might take a file handle and then return more effects from that, so that you want to keep like processing things. And so you can kind of do this over the entire API surface. So like read line, take the file handler, returns a maybe string. It might be the end of file or something. Same with close handle. And like close handle doesn't have a return value, it's just unit. Like the first argument to the callback is kind of like the return value of the function, or like the effects.
Is file handler here different than file handle?
Oh yeah, no, it's the same. I just typo. So yes, so they're the same. And file handle is just kind of like, we're just modeling. I don't know what file handle is. It's just some type somewhere. Same with std out. We're going to like print to our console, and it doesn't have a return value either. It's just unit. But we'll have more effects. We might have more effects we want to process. So that's like how we sequence things. It's just putting things in these callbacks. And also we want to be able to stop at some point. Program has to end at some point. Not all programs, I guess, but we probably want that. And so if we were to write a program in this style, there's like a sample of like, we're going to open a file, and we'll get the file handle out of it. Then we're going to read line with the file handle, get the next line out of it, and like print, maybe like read in a line from that. And so this is just kind of like a description of the effects that we want to happen in our setting. But the question then comes like, how do we actually run this? And so, because like right now we just have a data structure that like represents our program that we want to execute. But there's no way to do it. We don't run it. In fact, in PureScript especially, we absolutely can't run it at a language level. Like PureScript, the language, has no way of doing anything with this. We just have a piece of data. And so that's where you derive the idea that PureScript is useless. And in fact, PureScript is so useless, if you just take the language, the core language, you can like type in like a number literal or a string literal, but you can't even do anything with it. You can't add them. There's no way. PureScript, the language, has no way to add an int to another int. The only thing it has is literals, and then it has functions. So I guess you could like, you could encode things with functions. Do some lambda calculus stuff. But otherwise, it's just like why provide literals when you can't even like, you can like create an int, or like you can specify an int, but then you can't do anything with the int. So to that end, it's definitely valid to say that PureScript is definitely useless. But we need a runtime. So PureScript does not specify a runtime. PureScript, the language, exists on its own, no runtime, but it does have hooks. This is like kind of the idea that PureScript is polymorphic over its runtime. And so right now we specialize PureScript to JavaScript. And these hooks that PureScript has is through like what we call foreign declarations. And a foreign declaration is kind of a pinky promise that like we're going to declare this type, we're going to declare these sets of functions, and at some point when we actually compile and build our bundle, somewhere, somehow, these pinky promises are going to be wired up, and it's going to be actual code that we can call. And so that's how we plug in a runtime in PureScript. So we're going to start with maybe. So if we're going to be running in JavaScript, we got to figure out how we're going to start wiring things up to the JavaScript runtime. So we're going to call this effect type F. Foreign import data F, and that signature is it's a kind signature that says that it takes a type and returns a type. So that's kind of like our effect A. In our foreign declaration, you declare the actual signature, the kind signature of the type. And so we're going to declare some of our operations that we might need to start doing things with it. Pure F is just a way of lifting some value into F. Map F is a way to adapt like the output of it. So if we get like a string, well, maybe we want to just turn that string. Maybe we want to try to like parse the string or something. I don't know. And then bind is kind of like in that data structure we had, where we had the continuations. Bind is just a way of generalizing that continuation passing and putting it in there so that we can now sequence more effects on top of each other by putting in a callback. And this is just kind of like a sample, like wiring up in JavaScript of what this implementation might be. So this is just like, this is like our data, our effect is data, but like this data is kind of like contains our logic that programs the JavaScript runtime. F in PureScript is represented by just a function without any arguments. So it's just a thunk. Has a closure to variables and things that you might want to run. And then but it never actually runs them. It just builds up a tree of things to run. That's like key to pure functional programming. If we're just programming with data, then nothing can actually happen. And so the convention then is to have like a main. We have like an F unit. I won't come up with an example, but still can't run it. In PureScript, you'll never be able to, even though we have like a runtime, we have like this like wiring that we've set up, we still can't run it. In fact, PureScript can't run itself, but if outside of PureScript, in JavaScript land, which is our runtime we're targeting, we can import the code that PureScript generates, and then we can call it from JavaScript. So that's how we actually get things to happen. We wire things up on the PureScript side, but it's still just a pure value. Nothing ever happens. And then when it comes time when we actually want to execute it, we just import what PureScript has generated, what the compiler has generated, and then we can call it. So it's this idea, it's kind of like this pervasive idea in functional programming is that we build a representation of what we want, of how we want to model a problem domain. And then we apply a transformation over it to get us into some other, maybe something lower level, like maybe go from a higher level like idea of I just want to do these three things, but then I want to transform it into something that's like more open-ended. So I'm going to talk about just kind of effects in the JavaScript run. So the runtime is like, I think a lot of us are pretty familiar with JavaScript, but in case you aren't, it's evented in that there's a single event loop that happens at the start of a program. And like things come in and it's only single threaded, so like events will come in like a click or an input or some input from the outside world will come in. And it will dispatch it. And anytime we want to run something, we have to be careful not to block anything. Like we can't run like anything that takes too much CPU or like block on reading a file because it's single threaded, then that event loop can't do anything, it can't receive inputs. And so everything has to be non-blocking, which means that JavaScript has to have a scheduler. And so whenever we want to actually run an effect, it's kind of the same idea, is that we give something to the runtime with a callback, and that runtime will schedule it to run those effects elsewhere, and then when they're done, it can invoke the callback. So callbacks everywhere. Versus something like Python, where you have like, sleep blocks for 1 second and then prints. But in JavaScript you can't do that. You can't just block. So you have something like set timeout, where you give set timeout callback, tell it how long you want to run. The scheduler takes that instruction with that callback, invokes it, and then when it's done, it calls the callback, and your program will keep running. It's the same thing in PureScript with the JS backend. So like PureScript with F, which just represents kind of like the JavaScript runtime. It's the same idea. It still has callbacks, but it's a little nicer. But it's the same idea in that set timeout. You give it some block of code to run, and it will run that after the timeout. So another example. This is kind of it's just a toy example of getting content. So it gets a path. Like you have a file directory in Python. This is pretty nice and simple. And that it'll go through all of the files in a directory, open them, read them, put it in a file array, and then return the array. So this gets all the contents for the files in a directory. It's very short, very sweet. Versus something like JavaScript. This is just, it's fairly low level. This just uses some Node APIs, but kind of same idea, but you have to do all this coordination to get around the async nature of it. And there's actually, this is kind of advantageous because whereas in the Python version, you know, it reads each file one at a time. So it'll block, read one, then block and read the next one, block and read the next one. But in our JavaScript version, this actually uses a bunch of callbacks, kind of forks off all the requests in parallel. It does some of its own bookkeeping to know when it's done, when all the files have come back in, and then it invokes the next callback when they're all done. So this is actually more efficient because it's running all of our file requests in parallel. And the PureScript version of this is not any better. So this is the PureScript version of the same JavaScript. I think it's actually probably worse, significantly. I mean, it's the same code, same logic, but it looks terrible. You know, because you have to explicitly model all of like the mutation and stuff like that. But this is really terrible. So what do we need out of this? I mean, like, what do we want if we take this idea of we want to build a representation, and then we're going to transform it into maybe something lower level. We want to figure out what do we want to represent? How do we want to represent these async programs? And what sorts of features do we need? That can help us write more declarative kind of like async code that composes and builds together really, really succinctly and really nicely. And so number one is please no callbacks. Like nobody wants to do like the stair-stepping callbacks. And it really everything's kind of callbacks on JavaScript, but we don't want any visible callbacks. That's the thing. We really want easy concurrency, and by that I mean we don't want this. This is concurrent, and that'll make all of these requests out. It'll do all this processing, but this is not easy. This is incredibly tedious, and nobody wants to write this over and over again. So we want easy concurrency. Also, another one that kind of gets overlooked a little is like safety without boiler, or safety, just safety. So it's like if you've got all these like file requests out, what happens when something like you want to stop that? Well, then you got to do all the bookkeeping to kind of you know, cancel all these things out there and clean up after them and stuff like that. So ideally, everything that we wrote would have easy concurrency, but then everything would be safe as well. And so like if anything gets interrupted, then everything can get cleaned up automatically. We want the runtime to actually take care of all of that for us. We don't want to deal with all the boilerplate of cleanup. And so that's where AF comes in. So AF, PureScript AF, F is the synchronous effects, AF is asynchronous effects. And so that's where AF comes in. And AF is kind of a high-level library for dealing with asynchronous effects. So one thing we're going to go through kind of some of the high-level things that we want to model in our like asynchronous program. So one, if we don't want to deal with callbacks, then so bind was just this way of sequencing things. It takes this, you got one computation here, this MA, then you got a callback A to MB. So this takes one program here, then it takes a callback with the result of that and gives you a new program. Then it kind of like mashes them together, assimilates them. And we want this to be asynchronous. If we want to be able to write asynchronous code without callbacks, like with that nice like do sugar syntax where everything looks kind of straightforward and imperative, and like in our Python example, then we want bind to be asynchronous. That's an important feature. So here's kind of like the same idea. If I was going to translate this into app, like we want it to look something like this, where we can like read a directory of files and then just iterate over the files. This is almost exactly like our Python example, right? So we don't want to deal with any of like the callbacks. We want it to look simple as possible. So then the next idea of we want easy concurrency. We want to be able to fork things like our effects off in parallel and bring them back together. And that's where this abstraction of parallel. Parallel is a type class of PureScript parallel. And it's a way of, so if you have like a monad that is, or where bind is sequential, you can't really then have something, can't have The applicative is another way of doing it. I won't get too far into it, but so parallel is just an abstraction that lets you go from one thing that is sequential to another representation that is in parallel. And so that's what the parallel operation takes. The sequential representation turns it into the parallel operation. And sequential then takes the parallel operation and turns it back into sequential. So if we want to be able to do a whole bunch of things in parallel, we can turn them all into a parallel representation, run them, and then bring it back into a sequential representation to bring them all back together.
Is there an easy way to prove that something that's sequential can be made parallel?
Not. I mean, it's not done automatically. You mean it's like as far as just in general?
Like how
I mean, you prove that it can be made parallel by only supporting parallel operations. It's kind of like the idea. Like that's the idea of like. We have a separate representation for parallel operations so that when it comes to writing the program, you can only write parallel programs with them. So it's, that's the only difference. And so each unit from the sequential thing, turn it into parallel. Well, then you can then compose the parallel operations together. They all run in parallel. And you have one big unit left over at the end. You turn that back into sequential and you can get the result out of it. But so, here's some applicative operators of just in AF. And so this is just, it would just take a go function and it would apply, it would run the effect for it would read two different files and then call go with it. And it would run, because it's an AF, which is the sequential representation, it would run these in sequential order. So it would first read one file all the way, then it would read the next file, and then it would call go with those results. But if we use these operators, these concurrency operators, parallel, this now switches everything back over to the parallel representation, which is paraf. And so now the requests are run in parallel to read files.
How does this end up with JavaScript? Would JavaScript kind of force it to be done sequentially anyway because it's consuming?
Well, because it's I/O and the I/O is non-blocking in the JavaScript runtime, it forks off both requests at the same time, and the runtime takes care of running them in parallel or whatever in different threads. Like the runtime will do something like that. But because the main event loop is single-threaded, yeah, I mean, only one of them can come in at any given point. They can't come in at exactly the same time. It's just that this takes care of the coordination for you. So here's another example. Like, say we have a bunch of TV shows and we want to get their Wikipedia pages. So as a simple example of easy concurrency, you can use traverse get page over the TV shows. And right now, because it's traverse, this uses the sequential representation right now of ath. It would run each request one after the other. But you can just switch over to a different operator, partraverse, which automatically flips things over to the parallel representation for you. Now everything runs in parallel and comes back together, and you get all the results at once. So fastest page. When you're in the parallel representation, you can use a different type class called alternative, and that has the effect of racing things in parallel. So it'll run all of them. The one that resolves first, it gets that. That's what it takes as the value, and then it kills all the other requests. So this will get the fastest one, and then kill all the other requests that failed or that were slower. Par one of the map is one parallel operator. And this is in the PureScript parallel package. So this is kind of a general abstraction. Not just specific to AF, it's just AF hooks into it. So another kind of primitive is something called fibers. And this is kind of, so fibers are like lightweight virtual threads. They're kind of like green threads. It's a little bit not quite as involved as like green threads or like a threading system. So there's just lightweight kind of cooperative multitasking with virtual threads. And so we have these operators. So one is like fork ath. I'll talk about suspend a little bit later. It's a little bit different. But fork ath lets you take an ath computation and then fork it off, just give it to the runtime, the ath scheduler, and the ath scheduler decide when to run it. And then it gives you the fiber back, which says, okay, we've got this computation running somewhere. Think of it as running in parallel in a different thread. It's all single-threaded still, but conceptually it's in another thread. And with the fiber, you can then join it and get the result out of it. So this is also kind of like promises in JavaScript. Promises kind of like takes a bunch of ideas and mashes them together so that it's not quite like just an asynchronous model. It's not quite like a fiber model. It's just everything kind of forks off at once. You can, there's no pure representation for promises, but fibers are kind of like promises in JavaScript. It lets you run concurrent effects, but then it keeps the result around in the fiber, so you can always dereference it through join. And join is an idempotent operator. So you can join many times, and you get the same result back every time. It doesn't run the effect more than once. And suspend is just a special case that you think of fork as taking a computation, giving it to the scheduler, saying, you can run this whenever you want. I don't care when you run it. I'll let the scheduler decide. Suspend kind of does the opposite. Suspend says, okay, I want this to run in parallel, but I want to decide when it runs. And so it lets you get a fiber out of it, but the computation isn't running yet. And so whenever you join it, it then initiates. It initiates the asynchronous effects. And what this lets you do, it lets you do some knot tying. So like if you need a reference to a fiber before you run the effect kind of thing, you can do kind of this circular reference with suspend.
But it caches. So fork, how is cache?
Well, I mean, it caches in that it only runs the effect once and then keeps the final result around, so that whenever you dereference the fiber again, you just get the same result back.
Oh, so the ID for whatever path is actually your reference point.
Mm-hmm. Yeah.
It's like the generators.
This part specifically doesn't relate to generators. You can. It's kind of orthogonal. Like PureScript coroutines is another library, and you can plug app into PureScript coroutines, which is more of like a streaming generator type model. So this is orthogonal to that.
So suspend can call everybody forks.
Here, I'll have some example. Well, actually, I don't have an example for suspend, but we'll look at the fork example, and then I can talk about suspend and kind of give you an idea of what it does. You don't use suspend very often, but it's important for laws. So we have some like abstractions for kind of like this concurrency hierarchy, like monad fork, monad error, monad kill kind of thing. But so it is important for laws, one, but it's also useful in a few circumstances, less so than fork, but there's some cases for it that are really interesting. So I want to start to get an example of like how fibers kind of work concurrently. There's just this simple routine here of count loop, which is just takes a label and a timeout, and then a number to count from, or to count down from. And so this just does a loop where it waits for the timeout, logs what value it's at, and then it keeps a running tally of the sum based upon how it counts down. So this is just calculating some sum while also pausing in between each one. Whatever, it's kind of it's a silly example, but it's just a way to get some result out of a long-running computation. So our example here, it's going to fork two different instances of count loop, different parameters. So we'll get a fiber A and a fiber B. And so because I'm forking it, it doesn't wait for it to complete. It immediately returns a reference to the fiber. You can think of that computation as running off in some parallel thread, virtual thread. Same with fiber B. So then we'll log that we forked. Now we're going to join fiber A. One thing to note here is that fiber B takes significantly less time. So fiber 1 will do 1 second steps. Fiber B will do 6 second steps. It has fewer steps. So fiber B will always complete before fiber A. But we're going to join fiber A first and print the result, and then we're going to join fiber B and print its result. And so, yeah, I mean, it's similar to thread ID, but it's a little bit more of it's kind of a richer representation. So like a thread ID is just kind of an opaque identifier to some thread somewhere, to something that the scheduler is working with. And so you can do things with that reference, but fiber just then, because it has like the actual value with it as well, you can dereference it as a value. And so these things will just be forking, will be in the background. Fiber's forked. You can see B counts down. The effects are kind of interleaved. But A takes longer to complete. Because we joined on A, it won't log anything until A completes, and it'll log the result of A. And then it will join on B and log the result of B. So even though B completed first, because of the order in which we join these two things, it helps coordinate them. But so the idea of suspend then, suspend, I got a question about suspend. So fork is eager, it gives it to the scheduler decide to run it whenever. And really in practice, it runs it right away. So it'll immediately start evaluating that forked fiber until it hits an asynchronous boundary. But you can think of it conceptually, like the semantics of it is that we just give it to the scheduler for the scheduler to decide when to run it. It may be now or it may be in the future sometime. For fork. Versus suspend, we just get a reference to a fiber. This says this is in parallel, but we're not evaluating yet. Like we haven't given it to the scheduler. We haven't given any permission to the scheduler to actually start evaluating it. We just have a reference to the fiber. So it's not running yet. It won't run until we join on it. So once we join, the first time we join it, it'll initiate it, start evaluating it, and then it will cache its results. So this gives you can do like a pattern where maybe I have a bunch of resources I want to query, but I only want to do them on demand when I need them. So you can go ahead and fork off these queries or suspend all these queries in a data structure. And then when I'm ready to pull them out, like if user clicks on something, well then I can just dereference it, dereference the fiber, the suspended fiber, and it will evaluate it on demand and get the result back and then cache it. So that's a use case for suspend. But also it lets you tie the knot. So like sometimes you need to run an effect, but you also need to get a reference to the fiber before the effect runs. So this lets you suspend something, get a reference to the fiber, and then initiate the actual effects. So suspend is useful for a few cases like that. So we also want to support like an idea of interruption or cancellation. And that's with kill fiber, and this is just like any sort of killing, like kill a thread or whatever. You got something in a thread, you want to be able to stop it just in case. And so this is an asynchronous exception. So with an error in a reference to a fiber, you can then throw that exception in that other fiber and cause it to halt. So as an example, the same count loop. We forked it off, it's running. Then we're going to have a delay here in this fiber. We've got another fiber over here. We've got a delay in the main one, and then we're going to kill the fiber that we forked, and it will stop it. It'll actually stop the countdown then. So it might just count down from 5 to 4 and then stop completely. And then cleanup. So bracket is an operator that lets us, there's a few components to this. This is pretty dense signature. So but this first argument here, or the first parameter is acquisition. So we have a resource, a potentially sensitive resource maybe, that needs to be, this lets us acquire a resource, our resource A. Then we have a callback here that is our cleanup. So whenever we're done with this resource, this callback will then take it and dispose of it. And then we also have here what we want to do with that resource. So this just lets us, it's called bracket because you acquire, you run whatever you want inside of it, and then you clean up when that's done. And it returns the result. So this allows us to do kind of like this nice, kind of like similar to that Python API where you saw that with open file as F. That's basically just a bracket pattern in Python. So this here lets us do that sort of that safe resource handling. So we might have this API for working with files where we have a with file, and bracket, it'll open it, but then it also bundles it with the handler to clean it up. And so with this file, we can then run this block of code. We can acquire the resource, run this block of code, and then the handler will always be run. And this is safe, so guaranteed even with our async exceptions. So kill fiber, we may have a fork running in the background somewhere. It's got this file, and then we throw an async exception. Well, then the runtime, the AF runtime, we want it to guarantee that it will still run all of the cleanup for us. This is no matter how deep the stack, no matter how many forks you have going on, how many dependencies you have, they all get cleaned up automatically by the runtime. That's what we want. Another aspect of cleanup, if you have a bunch of these virtual threads running, you don't want them to just kind of go off on their own, to kind of have like zombie threads over here, like everywhere. So you may fork something off, but if you don't remember to clean it up, it'll just be running. It may be running like a poll or something. I don't know. That's common. It's a common pattern to fork a thread, run some sort of event poll, and then do some communication. But if we forget to clean it up, then we may be running even when we expect it to stop. So supervise is kind of a brain dead type signature. It just takes an AF and returns an AF. But what this does is it creates a scope for managing all these fibers or all these like virtual threads. And so when our main block of code here, our parameter, it runs our block of code, evaluates it, keeps track of everything that gets forked within that context. And then once it completes, it cleans up everything for us. So we can fork everything as we want, and then the runtime will make sure to clean up all of our threads in the background. We don't have to keep track of it. We don't have to do any bookkeeping. So in this example, we might fork off some delay with a log. But then, because these are forked, it immediately logs all done, and then this block of code is done. But so supervised will see that, okay, we still have these pending virtual threads, the fibers, and then it will automatically kill them for us so that we don't have to worry about cleaning them up.
Not supervised. What would happen?
They would just be running. Yeah.
When this completes, it exits, and then threads.
Yeah, the virtual threads are still running with the AF runtime. So it creates a safe scope for dealing with. Yeah, delay is just sleep. It's like sleep.
But then, like, let's say, presumably, like, I would expect it to. Oh, I see. I'm sorry.
Because the block of code, these are forked, they're running and they're supposedly running somewhere else by the runtime. But because the main block of code then yields all done, it's done with all of its work. These threads are still there, but they're still waiting, but it will clean them up for it, like without the supervised in. So like this will just log all done. Even though we forked something off and set in our fibers, it's going to log other things. Because we've supervised it, they'll actually get cleaned up for us.
You didn't supervise it and say all done.
Then yeah, exactly. Exactly. So supervise is an aspect of kind of like this easy bookkeeping. We don't want to have to deal with all of this manual bookkeeping for stuff. So child fibers can't outlive the supervision scope, and the pending fibers will be killed and cleaned up, so you don't have any loose ends. Then some other, I won't talk about this too much, but like this is actually a separate library, but like asynchronous coordination is avars, asynchronous variables, similar to mvars. So if you know anything about Haskell stuff, mvars is it's just basically a way of creating kind of like locks and doing like coordination. So like a variable can either be full or empty. And if it's full and you try to take it, then you get the result. But if there's no value in it, then it will block until a result is provided. So it just lets you do async coordination. But that's a separate library and not important to the semantics of AF. Just thought I would mention it. So what do our constructors what do our constructors look like? So this is again kind of a dense signature, but makeAF kind of bundles up. If we're building asynchronous things, like the only thing we have really is F. F binds to the JavaScript runtime, but it's synchronous and it uses callbacks. So we have to have some way of lifting these F callbacks into AF. And so that's what makeAF does. And it takes a function to run. The runtime gives it a callback where our effect can either give it an error, say like an error was thrown, or can give it a result. And then we can run that effect. We can do all of our own bookkeeping, and then we return what's called a canceller. And this is just whenever we run an async action, we want to provide some way for the runtime to clean up our async action, because it may take for any amount of time doing whatever, maybe making requests or something. we decide to kill the fiber that's running that, we want to be able to have some sort of cleanup action run. So this just lets us lift our primitive effects and then provide a way to cancel our primitive effects. So as an example, we're going to rewrite sleep or delay using set timeout. So we use make af, and it gets a callback. So we're going to call set timeout and resolve the callback with write. Set timeout yields a timer ID, and then we're going to return from this block, we're going to return our canceller, which clears the timeout. So it unschedules the timer. So this means we can just do something like this now. Because we've lifted this primitive effect with callbacks into af, we can now use it without callbacks. So we can just do something sleep, just like the Python API.
I'll make sure.
No, it'll make sure. So if I take this example and in another fiber, if I fork this off, and then I throw an asynchronous exception into that fiber, the canceller will be run and clean up the timeout, or clean up the timer.
Things in af kind of are always forced to already have the canceller involved. Is it
Mhm.
common to use bracket? That pattern's already
It's
already kind of baked into it.
So this is only for primitive effects. So bracket is a generalization when you're building things just on top of app. So if you had like an open file operation, canceling it may not have exactly how you're in the acquisition phase of bracket, and that can't really be canceled because you have to acquire it. You can't really cancel something that you in the middle of acquiring. So I don't remember for sure. I don't remember how I wrote it, but I don't think like acquisition can actually be canceled. It'll block until that runs, and then it will cancel. Then it will run the cleanup, and then so cancellation always just like cleans up everything that it can based upon the cancellers that you provide the primitive operations. And bracket is a generalized way in af to attach various cancellation behaviors to just arbitrary af computations. So bracket, there's a generalized form of bracket that lets you observe whether your block of code exited normally, whether it threw an exception, or whether an asynchronous exception was thrown in the fiber, and you can do different cleanup based on that. So that lets you run different code in different situations. And so this lets you, the bracket pattern lets you attach arbitrary cancellation behavior to af code, and canceller is just a primitive thing for our basic af building blocks. And so the other kind of constructor is just this ffn af. And this just lets us write FFI functions and lift them into af. So we might have a foreign import for my af, but we type it as ffn af, we lift it into af, and then our foreign import might just be this sort of like callbacky representation. It's kind of like how promises are represented. They take like an on error, an on success callback, or like a reject or resolve. And it does something async, it will call the success or error, and then this is a representation for cancellers. So it'll get the error that was thrown, and then you can call back whether cancellation was successful or not. So what is our, like, I talked about kind of like this idea of like, we build a representation. This is kind of going through the high-level API of what we would like to work with. And so the representation app is opaque because it's really all JavaScript for performance reasons. But it is a data structure. It's a data structure really similar to what we did earlier in the talk, like with that kind of like read file API. But it's just for all the primitive operations inside app. And this is kind of basically, this is dense, obviously, but all of the operations are modeled as data in the same kind of pattern that we did before. We lift up our callbacks into this data structure. And then we have our transformation here, run app. It'll take this data structure we've built and it interprets it into the underlying JS runtime bindings. And the callback here would be that's the thing that you run when your app is done, because it's JavaScript now, it's an F, but you have to use callbacks in that case. So our AF representation that we have, we just modeled it with data, and it has all the features that we want. And then we have our transformation function, run AF, transforms our data structure, our representation of these async programs into F via callbacks. And so this can be run by the JavaScript runtime. And so you can even take this idea further of, like if we're in an application or something, maybe we want to only model the effects that are in our application. So we don't want to run maybe arbitrary effects. Maybe we want to run like, maybe we have like a REST API or something. We just want to model the request directly to that REST API. Well, then we can use the same pattern, maybe through free. PureScript free is just a general purpose kind of data structure that lets us build pretty easy DSLs using the same sort of pattern and writing interpreters for them. And also PureScript run is another library that lets us build extensible DSLs, so we can have different components over here, different components over here, and then compose them together really easily. And then that's it. So, meet Faubion on GitHub. But any questions? I mean, it's a lot, but do what? The performance is really good, actually. So originally, AF was, the representation was just callbacks. Like, from everything was just callbacks. And it looked a lot like promises. And so because it was just callbacks, it was pretty fast, but it has a lot, when you're using just callbacks, you have a lot of limitations, and especially like for stack, because you're just calling callback one after the other. If they all resolve synchronously, you'll blow the stack. And it was fast, but it was fairly unsafe, and the implementation was really bad, or really hairy. It was like, we could barely reason about like what it was actually doing. So it's now kind of written in this direct interpreter style, where we model our program with the data structure, with all the operations, and we run a single loop, interpreter loop, over these instructions. And so we'll pop off the first instruction, interpret it, run the effect, get the callback out of it, run, and just run this in a loop where we just pop things off of this instruction set. And it's actually significantly faster than the old way. So even though we're doing more, where we're actually building a data structure, we still have like the spine, the data structure of our application. And that representation seems like it's heavier. It's really not in practice. So like when you're doing callbacks, you still have to allocate like heap objects everywhere. So you got to keep things in closures, callbacks, but now we're just putting it in an actual data structure. And it's actually significantly faster. So I think performance from the old one, it's about 1.5 to 2 times as fast as like the old callback approach. Just using this we use this hot while loop over our instructions. And I don't really know how to what to compare it to, but it is, for what you get out of it, it's always stack safe. That's one thing. It kind of goes back to the safety aspect of it. Is that I don't want to have to I don't want to fork off 1,000 parallel things and then think they're running in parallel, but they just eat stack. And that's kind of what would happen with the old AF. Is that if you ran parallel requests and you ran too many of them, they would all blow the stack, because they'd all, depending on if they were synchronous or not, they would blow the stack. And so a lot of pains to get stack safety pervasively.
Nicely to Erlang and C++ then too, because of the reasons?
Kind of, not really. So part of the problem with AF is that it assumes that you're using callbacks, and that's really kind of a JavaScript limitation. If you're in a different language, you can probably just bind to F directly, because it has synchronous things that you can run, and actually then it has primitives for multi-threading. But since JavaScript doesn't have that, you can port it. I know Hardy Jones did some work porting it to Erlang, but it's not really necessary in Erlang. It's the kind of thing. It's like Erlang is already a concurrent runtime. And so it's like we don't need to build another concurrent runtime on top of a concurrent runtime. So, but you can. And so you could imagine. I know John DeGoe's. We kind of went back and forth as this was developing, and he was doing Same kind of thing for Scala, like Scala Z, like the IO library that he wrote. And so we ping back and forth. And so they're basically the same, there's very similar API. And so you can run it in JavaScript with this API and basically the same API running in Scala as well, with actual threads. It's got like thread pools and stuff and does all of that scheduling for you.
A little bit more about that.
So there's PureScript app, like the GitHub repo. Otherwise, it's just trying to use it. I mean, there's some examples, but yeah, as with all things in PureScript, documentation can be better. But yeah, well, I mean, you just got to start. It's the kind of thing you have to start using it.
I've been using it, but I'm sure what type checks.
Yeah.
Not really good, but
Yeah.
Yeah.
Yeah. Yeah. But yeah.
was there a particular inspiration for? It sounds like a pretty significant switch to just modeling after interpreter of like representing all of those actions as data types instead of just as like a function line, but actually as a data type line. Was there a particular inspiration for that?
So originally, the original issue was I wanted to write as much as I could in PureScript. Like we wanted to, because it was all FFI before, it's still all FFI now. But the idea was, okay, we want to write this in PureScript. So how are we going to do this in PureScript? We're not just going to write F callbacks everywhere. And so I started modeling it in PureScript as a free DSL, so like PureScript free. And so I just put all the instructions in that and wrote an interpreter over it. And for being in PureScript, it was actually surprisingly fast. I think it was like maybe half the speed. It wasn't bad, but it wasn't great. So we just ran with, just ran with that. But it's just kind of like, I don't know. It ended up being a nice approach, fast. When you actually write it in JavaScript, I don't know, it was easy. Not easy, but
So a lot of the
I felt like it was clearer than the old approach.
a lot of the machinery is involved is PureScript free.
No, that was kind of like the intermediate version, like the demo version that I wrote. I was rewriting it in PureScript, but we actually wanted it to be faster than the old version. So we rewrote it in PureScript. It was a little bit slower, but we wanted it to be faster. So I rewrote it in JavaScript. And the same approach, but in JavaScript, with JavaScript data types and like JavaScript optimizations. So, but yeah, it's basically, AF is basically kind of what I call like an ad hoc free structure. So you have like all like the bind and stuff suspended in the data structure, which is just what free does. And so, yeah, it's just kind of its own little free, in its own world that kind of looks like free and an interpreter over it. Just whenever you're writing things in F, because it is data, it's the memory pressure is higher. So each effect is like its own little closure, which is a heap allocated object, and you just end up generating a lot of that. Like the F binds create a lot of heap objects, and so it's slower just because GC pressure. And that's something that I kind of hit a lot with sort of high performance PureScript stuff like virtual DOM library, and just a lot of GC pressure based around that. And that was kind of like I think that was the main thing slowing it down. So like one thing about the JavaScript interpreter is like the fast path of it, of just like interpreting binds and pure and stuff like that, is allocation free. So it's a hot interpreter loop that doesn't allocate at all, and so that makes it insanely fast. The allocations are one of the biggest slowdowns in something like this. And so a lot of care has gone into making sure it allocates kind of as little as possible and can do as much. So it's written in kind of like a C style JavaScript where you have like registers and things like that. And so it's kind of like the implementation looks pretty primitive, but it's very fast. I can show you it if you want, but it's really hairy. it's not. It's better than it was before. Like when you actually read it, it's not that bad. But it just like at first glance you look at it and it's just like, whoa.
I'd be curious for a quick snapshot.
Yeah. Let's see. So this is kind of like is our approximation of the types. So it uses this kind of these are all like the tags for it for all the things, but it uses this universal constructor here where everything is the same size and has the same structural hash. So that's how JavaScript does it, or a lot of engines do optimizations, is that when you have a constructor, it takes kind of a hash of the properties and what order they're in, and then it caches the lookups so that if it always hits the same structural hash, then it can dereference the thing in memory directly instead of running like a hash lookup or something. So everything uses this kind of like universal structure where every object is the same size and has the same properties. And so versus like in PureScript, if you had a lot of different constructors, they're all different classes in JavaScript, and you can get cache hits that way if they're represented by different structures. And so that's our like bare bones scheduler. It's our supervisor. This is all the bookkeeping for fibers in a supervised scope.
Is there any?
And then here is our main interpreter loop, fiber. This is where all the magic happens. And it just goes into this hot loop here, this run loop. So one thing with callbacks too is like dealing with resumption. Like if you call a callback multiple times, and so it has to take care of that. You can't call a callback more than once in AF, like the low-level callback. But so it's just steps over each instruction. This is kind of like these are actually our states. It's like a state machine loop, and so it just puts it in. Like these are our registers, like B head, B tail, like bind head, bind tail. It keeps a stack running. It has to keep a stack as you like go into a different like a try catch sort of thing. And you have to keep track of all the stack state and stuff like that. So it's just pumping through the states, and these are our instructions here, like pure, sync, async. So this is an async effect. So also an AF, because we want to preserve. So lift F is how you lift effects, or like the F type into AF. And so we want to preserve the transformation of if we have two lift Fs, we want to be able to transform that into a single lift F where the effects are sequenced in F. And so we do some work for that. So we make sure that if we have only synchronous effects, our AF executes completely synchronously, as if it were written in F, but it's safer because it won't blow the stack. And it uses async is when it runs async effects with the callbacks. And this is where we do our kind of scheduling at async boundaries. This is what this scheduler enqueues a new task. So, yeah. It's just long, it's just through each state. So it's just mapping each state to some new state bracket. This is how it handles brackets. There's some internal instructions too, like this is what this release is.
Make me feel better.
Hmm?
This isn't making me feel better.
That's the thing, though, is that this is doing all the work for you, all the gnarly work for you.
I'm not supposed to see it. It's awesome.
Yeah. But sometimes you have to kind of like see how bad it is to appreciate it. Yeah. So anyway. And all this stuff is just for like stack safety. It's like, oh gosh. So like the parallel stuff, if you want to, since I wanted to make sure everything is stack safe, if it's supposedly running in parallel, if they're all resolved synchronously, they all call callbacks. And so normally it creates like you have this tree of resolutions and it'll just get a deep stack. And so like half the code is just dealing with stack safety in RF. So anyway. Scan.